1x0, 1x0 to z, then you can include the what? Turnout delay. Are you understand this? So these are the gates are specified with the gate delays. Gate delays are rise delay, fall delay, and the turnout delay. So this is an example which we have done with both the rise delay and the what? Fall delay. So rise should happen after the what is the delay specified to the gate. Fall should happen. What is the delay I have specified to the gate. So this you can easily modify. Now you can give the range, means minimum, typical, maximum range during the runtime to modifying the values of the delays. To experiment with each delay, what is their performance. Are you understanding regarding this? The delay which is associated with this. Is it clear? Okay. So this is a program with the delays. Okay. Now let us start with few examples. So this another slide is an explanation of this. Okay. So these are the delays. 3 delays which is associated with the primitive gates. Okay. Now let us take few exercise on gate level modeling. Then we'll go for the data flow modeling. Now you can see this is a program. I'm asking the logic diagram for the RS latch with the delay. So what delay I'm talking about here? Hash 1. Hash 1 means what is this is nothing but. It includes all 3 delays: rise delay, fall delay, and the turnout delay. So rise delay means what? Whenever your signal changing from what? 0 to 1, or x to 1, or z to 1. Fall delay means 1 to 0, x to 0, or z to 0. Turn off, you know that. So 1, 0, x to z. Okay, this is a delay specified to this. What is this? Is nothing but this circuit is nothing but SR latch. SR latch. So this is a program I was asking you. So write the Verilog description for the RS latch. Okay. Including the delays of how much? 1 unit delay. 1 unit delay. When instantiating the NOR gate, write the stimulus module for the RS latch using the following table and verify the outputs. So when set is 0, reset is 0, it is acting as what? Memory state. So Qn plus 1 is nothing but the next state. This is a next state. Qn is nothing but what? Present state. If S is equal to 0, R is equal to 0, no change in the circuit is nothing but this state we call it as what? Memory state. Our previous state as before state. S is 0, R1 means what is this state is nothing but reset state. S1, R0 means what? Set state. S1 and R1 is nothing but what? Violation state. Correct. It is not giving the predictable output. Correct. Unknown state or undefined state or a forbidden state. Can you write a program to this? Write a design file for the RS latch. Okay. And with the delay. Hash 1 delay, rise delay, fall delay, and the turnout delay. Also write a stimulus block and verify the result of this SR latch. So how to write a program to this? How to write a gate level modeling to this? Using primitive gates, right? So let us write, what is this is nothing but module. Module name is nothing but what? Shall I take SR latch? What are the outputs are? Q1, Q bar, what are the inputs are? R and S, correct? In this case, what are the input are? R and S, output are Q bar. Q bar. Correct. Next, what I need to do? What gate it is? What primitive gate it is? AND gate or NOR gate? NOR gate. NOR, correct. So he is talking about with the delay. Correct. This is nothing but hash of 1. Hash of 1. Then shall I write the gate 1? What is the output to the first gate is? Q. Input is what? Q bar and R. Correct. Next, NOR. This is small n, small n NOR. What is the delay of this is nothing but hash 1. This is G2, Q bar, comma, Q and S. Then what I need to do? In the module. Now write the test bench to this. How to write the test bench? What will keep be reg R and S by Q1 Q bar, instantiate the design file, then initial begin, generate the inputs, display, and get the output. So this is one program I am giving as the exercise. First you do without a delay. First you understand write a SR latch without a delay. Okay, remove the delay and see the output. Write the test bench and see the output. Or to understand. And next you should include with what? Delay of how much it is. As much. Raise delay, fall delay, and turn off delay. Are you understanding this? You write a stimulus and in design file and verify the result of SR latch with the delay and without a delay. Both program you can write. Okay. This is a one question. The second question is, so design a 2x1 box using BufF 0. BufF 0. What is BufF 0 means? Buffer with active enable. BufF 1 means what? Buffer with active enable. So this is a BufF 1, right? Active enable this is. BufF 1. BufF 0 means what? Active enable. So using buffer you should design the one. 2x1 multiplex. Using BufF 0 and BufF 1, gates as shown in the figure. This is an input IN0, this is IN1. So how this is acting as a multiplexer here? When select line is equal to 0, correct? Which buffer will be turned on? Buff 0, correct? Since it is active low enable, now this is acting as a buffer. It is like acting as a short circuiting. Now whatever the input I am giving, it is selecting at the output. The same time, what is this buffer output will be? Z. Z means what? Floating state, high impedance state. When S is equal to 1, what it has to select? 2x1 multiplexer. I1 should be selected. Right? In this case, I1 will be on, and this should be what? Open circuit, not closed circuit. Therefore, output is equal to what? In 1. It is selecting the I1. S naught is 0, I naught it should select. S is equal to 1, I1 it should select. Did you understand this? Now, you can see, along with this, I am giving the delay specification for the gate B1 and B2. B1 means BufF 1 and B2 means B1 is BufF 0, B2 is nothing but BufF 1 as follows. So I am giving rise time is, minimum rise time is what? 1, typical value is 2 and maximum value is 3. And for fall also, I am reading what? Minimum is 3, typical is 4 and maximum is 5. And turn off also minimum is 5, typical is 6 and maximum is equal to 7. So apply the stimulus and test the output result. Apply the stimulus and test the output values. So these are the two examples which I am asking to do with the delays. Okay, primitive gates with the delays. So I have mentioned all the typical value, minimum value and the maximum value. Did you understand this? Now let us go to the next question. The next question is, this is the one. What is the question is, implement the 4-bit comparator. 4-bit comparator using what I am asking about? 4-bit full adder using the structural modeling. What is structural modeling means? Gate level modeling is also called as structural modeling, correct? The structure means, suppose I want to build a 4-bit parallel adder. What is the structure is? Half adder. Use the half adder to build the full adder. Use the full adder to build the what? Parallel adder. There is structure in this, correct? There are hierarchically we are doing half adder, full adder, then parallel adder. Okay. That is nothing but structural modeling is also called it as one. Gate level modeling. Now, could you able to analyze this circuit? This is nothing but your 4-bit parallel adder itself. 4-bit parallel adder itself. Use this 4-bit parallel adder to design the what? Comparator. How to build a comparator using 4-bit parallel ladder? Comparator means what? Comparing the bits. 4-bit means the magnitude is 4 bits. So what are the outputs of the comparator is? A is greater than B, A is equal to B, or A is less than B. How to write the logic to this using the gate level? For A is greater than B, A is greater than B, A is equal to B, and A is less than B. How to write the logic to this? Using 4-bit full adder, you have to design this comparator. Here, A3, A2, A1, A0 are the minuets, correct? There is nothing but a minuet. And B1, B2, B0, B1, B2, B3 are the what? This is subtrahend. When you say that A is greater than B, at what condition you will be getting A is greater than B? If minuend is greater than the subtrahend, correct? I can take this is a scalar, 3 down to 0. This is B is nothing but what? 3 down to 0. When you say that A is greater than B, if minuend is greater than the subtrahend, then you can say that A is greater than B. When you say A is equal to B, minuend is equal to subtrahend. That is A is equal to B. So when you say that A is less than B, minuend is less than the subtrahend. Correct? How to do this program? How to do the gate level modeling for this program? What is the logic to this? Using 4-bit parallel ladder, I have to design the component. Gate level modeling technique. So when you say that A is greater than B, the condition is that you should get C out is equal to 1. Correct? C out is 1 means A is greater than B. Correct? Are you understanding? When you say that A is less than B, so if you know if you are performing A is greater than B, if you are performing A to B, there is a relationship between the comparators. Means A is less than B is equal to A equal to B, NOR gate of A is greater than B. So to know this, you construct the true 2-bit comparator and check this. This relation is true. Or you can write A equal to B, you can also write A equal to B is nothing but what? A is less than B, nor A is greater than B. And then A greater than B is nothing but what? A equal to B, nor A less than B. This relation. So when you draw the truth table of 2-bit comparator or 1-bit comparator and verify this, there is a relationship between A greater than B equal to B or A less than B. Okay, I am giving the hint to solve this, write a program to this gate level modeling using 4x1, 4-bit full ladder, means parallel ladder. So when you say that A greater than B means, when you get C out is equal to 1, that gives the what? A greater than B. When you say that C out is equal to 1, you tell that this is A greater than B. You understand? When you say A equal to B, when you say A equal to B, if this is some S0, S1, S2, S3 or 1, 1, 1, 1, then that becomes A equal to B. All these 4 output, what you can do, you can put through AND gate. This gives me what? A equal to B. Then how to get the A less than B? What is the relation between the A greater than B is? A equal to B, nor A greater than B. So if you take this is A greater than B, this is nothing but A A equal to B, NOR gate, this will gives me what? A less than B. So I am giving a hint to you how to find out greater than, less than, or equal to. Verify this logic and write a gate level program to comparator using the parallel ladder. Did you understand? So you can take these questions and also you can take few more questions. I think these questions you can easily create. Create the own two input Verilog gates called my OR, my AND and my NOT from the two input NAND gate. Means this is nothing but you are going to realize the AND gate, OR gate, NOT gate using what? Using NAND gate. Using NAND gate. You can understand? Now next question is, this is the one. The two input XOR gate can be built from the my AND gate, my OR gate, my NOT gate. So already you designed the AND, OR and the NOT gate using the NAND gates. Construct the XOR module in the Verilog that realizes this logic. This is XOR logic. XY bar plus X bar Y. Input are XY and output is Z. Write a stimulus module. Exercise all the four possible X and Y outputs. You can understand. These are another question. Yeah, any doubt in this question? So what you need to do? You need to do the two input XOR gate can build from the one. And my AND gate, my OR gate and my NOT gate. This are already you build above using what? NAND gates. Then build the XOR. This is another question. And then you can go ahead with this. I think this question already we have done. This is a 1-bit full adder. Okay. So 1-bit full adder, this is my sum expression, this is my carry expression. So we have done this, right, already. 1-bit full adder. So when you are doing the parallel adder, 4-bit parallel adder, you are instantiating what? Full adder. Full adder you are done using half adder. But here they are asking to write using what? Logical expression. This is the sum Boolean expression. This is the carry Boolean expression. You can build this circuit using the gate level. Okay. So can you write a program to this, all these programs, and then another program, this is the one I was asking. One more is nothing but 2x1 mux using buffer. And one more is nothing but use the 4-bit parallel adder to design the comparators. So you can write a program and bring me the programs tomorrow. Okay. So this ends the gate level modeling technique. In the upcoming sessions, we'll go with behavioral. One of the higher level of abstraction is nothing but behavioral level modeling technique. We'll start from the next session. Okay. So you should write a program to this. You try at your end. Anything you are not getting, I will be there. I will be helping you to write the program. Okay. But you should write a program and bring it tomorrow. Is it clear? So with this, I will be stop the session here. So we will continue in the next session. So now I request all of you to fill the attendance. Attendance is done. Online student, I request all of you to fill the attendance. And any questions are there, you can please go ahead now. Okay, try this today and get me the program too.